First thing on the agenda for today is to go over problems 1 and 2 in the homework. And to tell you that you will need appendix airplane D, as in Domino or David, for the exam on Monday or Tuesday for the exam. Airplane D, like as in ABCD. These problems look at airplane B, and we're calculating perturbed aerodynamic forces and moments. So really, this is just your ability to convert, plug in numbers, and check with a computer. So I want you to do this by hand and also put the matrix into MATLAB or Maple. So the first thing to check, here's the longitudinal. So we have to calculate all of these values in this column. So check that first. And then we'll come back to the lateral directional. So here's the cruise condition, the area, all of the data for the airplane. U over U1 should be 0.048. And then we have to do alpha dot C bar over 2U1. And this is not dynamic pressure, this is pitch rate, Q C bar over 2U1. And we need alpha in radians and delta E in radians because the data in the back of the book is all in radians. So those are the values that go in the right hand, the column vector in the matrix. So they're copied in this column here. And then these are the values pulled out for all of the small perturbation derivatives from the book. So again, those are the values that go in there for all of this stuff here. Remember, if your book has the typo, make sure you fix the typo. Instead of an L there should be a D. Let's see. Okay, so here we are. So I'll give you a minute. If you have worked this, hopefully you tried it to check your numbers. And then the answer is multiplying this vector times this matrix. So let me see if I can get both on the screen. Here's the answers. FAX over Q bar S is this value here. FAZ over the, essentially this is the coefficient. And then you should multiply by Q bar S and get these values in pounds. All right, let me know when you're good and I can move on. And then there's the pitching moment answer down here. So when I grade this, I'm going to be less looking for you getting the right answers because I've given you the right answers, and more for you making sure you show me your work. Show me the conversions. Show me the matrix filled in, the column vector filled in, and show me the answers. So we need to do the lateral directional. Can I move to that? Good. So here we have to calculate beta dot non-dimensional, P non-dimensional, R non-dimensional, beta, aileron, and rudder. And they're the values that go into the vector, just like before, for the longitudinal. And there's no units on any of this stuff unless you are willing to write radians just to make sure you know that you don't have it in degrees. And then those numbers go into the appropriate places in the column vector. Fill in the numbers from the appendix. And then we calculate the side force, rolling moment, and yawing moment. So here's the value for the side force, coefficient, the side force. I'm going to scroll down and so unless somebody jumps up and shouts. So here's the answers. And here are the perturbed thrust forces and moments. So we have to calculate U over U1 and alpha in radians. A lot of the values here are 0, so the only one that actually goes in is this one here. And you get an X thrust force of 23 pounds. And you go 23 pounds, that doesn't sound like very much. Remember, this is a perturbed force on top of a steady state force. So this is a perturbed thrust force direction on top of the steady state. And then the beta terms are all 0, so you just get 0 for that. And today we'll go over where the numbers that go into this matrix come from. And then that was actually part B for number 1, although I had it labeled 2. And then problem 2 is to use the estimate equations for CM alpha dot and CMQ. So these are vertical tail effects. So I've given you some data, and then you need, horizontal tail effects. And so you need the lift curve slope for the horizontal tail because they're horizontal tail effects. So here are the 2 equations from the vertical tail, I keep saying that, horizontal tail effects. We need the moment arm, horizontal moment arm, and this is non-dimensionalized with respect to Q bar S. We're going to use 8H of 1, here's CL alpha H, and then we need the distance from the CG to the aerodynamic center. So this is where your answers may be slightly different than mine. You go to the figure for the airplane, and I got this value for the distance from the CG to the aerodynamic center of the horizontal tail. Is that close to what you guys got? Again, this is non-dimensionalized with respect to C bar, so you have to measure the distance and then divide by 4.79. This comes from the picture here, so that the distance that we're doing is this distance like that. So I physically measured it on this diagram and then used this scale ratio. This is 17 feet, so you can use that. That's probably the best distance to use to get the scale on the drawing. And then we need the area of the horizontal tail, so I took the root chord plus the tip chord and added them together and divided by 2 to get an average, and then multiplied by essentially by the span. So that's where those numbers come from. So VH bar should be this. And then SH is that number I just showed you how to calculate. I got 54.5. So you plug that data along with the other numbers that you already have, and you get a CMQ, a minus 27.14. And then the data in the back of the book has 26.3. That's pretty good, right? CM alpha dot, multiply that out, and you get this number. And the data in the back of the book has this number. So that's not good. So what's the difference between the two? It's this number here. So that means the number that I gave you for the downwash model is not good. It's not as good as it should be. That's where the difference is. Also, there's a little bit of wing effect, and this is just the vertical tail. So the suspects for the difference are d epsilon d alpha, because that's the difference in the formula here, and the fact that the wing could be adding to this effect. Although not much. So this is the kind of thing that sometimes you'll do in industry is you'll run predictions for a design for an aircraft, and then you'll go into a wind tunnel and measure values and they won't match up, and you'll start looking as to, well, what's wrong with your predictions. All right, so these, along with everything else, well, it's really just one more problem. Doing something similar, lateral directional here, are due on Monday before class. Then it's not Monday, Tuesday. And then we'll do a short exam, a 30-minute exam, and then we'll continue on. Any questions about what's happening next Tuesday? Yeah, I told you which ones. Oh, yeah, anything else you want to bring? The stuff we've covered, sure. Okay, continuing on with the lateral directional forces and moments, we're down to the small perturbation yaw rate. And the non-dimensional version of this is just like we did with P. It's RB over 2U1. And we're talking about CYR, CLR, and CNR because the side force FAY, small perturbation, is just CY times Q bar S. So we just talk about these derivatives here. So we're going to start with this one and then work our way down. This is mainly a vertical tail effect. This one has a vertical tail effect and a wing effect. And this one has a vertical tail. In fact, this one is one of the reasons the vertical tail is there. And there's also a wing effect. So let's work our way through that. Starting with the foam airplane of flight dynamics. Which for a day was on the injured reserve list because I crushed the vertical tail in the drawer that I keep it in my office. Fortunately, a little Elmer's glue glues this thing back together. So we're talking about yaw rate now. So we're talking about the airplane yawing positive nose right because Z is down, nose right is positive. So we're talking about the airplane rotating like this, which means the vertical tail is sweeping this way. So we're going to get a dry erase marker force vector in that direction because of the change in angle of attack of this thing. It's still flowing, there's still air flowing this way, but as we create a side velocity of the tail, we change its angle of attack, so we get a force in this direction. Sorry, did I do that? I did that backwards, shoot. So we're rotating like this. We get wind coming in this way, right? So our force vector is this way. I'm standing on my head. So we're going, yeah, this way. And so which way is that going to provide a yawing moment or a side force? It's going to provide a positive side force. It's going to provide a negative yawing moment to stop the yaw rate. And it's going to provide a rolling moment that we have to decide, is that good, bad, or we're just a side effect? So let's go through that again because I got my head turned around. So we're yawing positive like this. Air is pushing on this side of the tail, so we get a force this way. It's going to stop the yaw, slide the airplane this way, and roll it this way. So here's a picture of our airplane. There's the vertical tail. The vertical tail is moving down that way, so we have a relative wind equal to that coming up this way. And that's created by this circular movement around the CG. Here's positive yaw rate like that. And so the moment arm here, XVS, the further the tail is back, the faster the tail is going to be moving at the same yaw rate. So this incremental velocity due to the yaw rate is R times XVS. And again, that's just the equation of a circle or an arc length moving. And so we predict forces with angles of attack. So the change in angle of attack is that side velocity divided by the forward velocity, because that's just trig. And again, we really ought to be using tangent here or sine, but we say tangent and sine of a small angle are just the values. So this is where R shows up in the side force, because this side force can be calculated from that change in angle of attack times the lift curve slope, and that gives us the force. So that's exactly what we do, is we say, okay, FAY due to R is CL alpha V times this delta alpha times Q bar V SV. So this is just the part due to R. If we wanted to calculate the rest of it, we'd have to put an alpha V in here. That would include beta and everything else that creates alpha V. But let's just stick just due to the R part. And so we want to turn this into a coefficient, CY. So let's plug in delta alpha, it's R, like that. Q bar VS, and we divided by Q bar S. And so the R effect is just everything that multiplies R, or the easy way to find it is to differentiate. You can think of it either as factoring the R out and everything that multiplies R is what we're looking for, or it's just the derivative because it's a line. So let's see, I need a little more room, so let's jump up here. We have to remember that CY subscript R means the derivative with respect to RB over 2U1, so that gets us this stuff outside like that, right? So again, whenever you see subscript R, you think it's that non-dimensional R. So we look at the CY, and it just means everything else here except for the R is what we're looking for. And again, conveniently, because we planned it that way, the U's cancel out, and this is a number that doesn't depend on the velocity. So how about the rolling moment due to yaw rate? Well, with the foam airplane, we saw that there's a vertical tail effect. So write this down, CLR, we're going to look at a vertical tail effect, and then we're going to look at a wing effect. I'm leaving my airplane up here because what creates the rolling moment is that side force vector that we just calculated, effect, times the vertical distance. So really, we've already done this. We've got CYR, that's the force due to R. We just multiply by that vertical distance, and we've got the rolling moment of the vertical tail part. And in fact, we multiply by the horizontal distance, and we get the yawing moment part. We'll do that in a minute. So this is easy. The vertical tail effect, CLR, it's just that ZVS, that vertical distance, non-dimensionalized, times CYR, and it's going to be positive because we've proved that with our foam airplane. And it's because the moment arm is positive up this way and the force is that way, so it creates a positive rolling moment. So the formula for this looks exactly like that, just multiplied by this stuff. And again, just like in the longitudinal, we look at this and we go, oh, wait a minute, look at CYR. This is a force, but there's a moment arm in here. And then we look at this and we go, well, this is a rolling moment, but we've got two what look like moment arms or distances in here. And we remember, well, where did they come from? The X in both of these comes from calculating delta alpha due to the yaw rate. And then the Z here comes from actually calculating the rolling moment. So it all makes sense. And then while we're on this, we can calculate Cn in the same way, except instead of using the vertical moment arm here, we just use the yaw moment arm, X. So we're going to end up with a double X. And again, these are both just the vertical tail parts. And you'll look here and you go, well, there's a minus sign here and a plus sign here. What's the deal? Well, the force, the positive side force effect gives a positive roll because the aerodynamic center is above the CG, but a negative yaw because the aerodynamic center of the vertical tail is behind the CG. So it's just location. So the key to any of these vertical tail effects, whether it's the effect of beta or the effect of roll rate or the effect of yaw rate, they always look like this. It's like you take the effect and you figure out how it changes the angle of attack. P changed it due to P times Z divided by U1. Beta changes it just by adding in beta. R changes the angle of attack of the vertical tail due to this. And then you build up from there. So we get a change in angle of attack. I still don't have that. Change in angle of attack times the lift curve slope times Q bar S, and then you're done. There's the force. And then if you're doing a moment rolling or yawing moment, you find the appropriate moment arm to multiply the force by. So really, this is just statics. Force times distance for moments, and force is just force. What complicates it is all of the forces are generated aerodynamically, so you have to figure out the aero model for the force. All right, so next is the wing effect due to the yaw rate. Yeah. Which one are you pointing to? CIR. Talking about this? That's CY, yeah. A CL. Yeah, it's this. Did I lose that? No, it's in here. Oh, yes, I lost it out of this, didn't I? Because CY had CL alpha V. It's in all of those. I dropped it off, right? That's what you were saying. Yep. Okay, so now we're going to look at the wing effect. How does the yaw rate affect the wing? So we're going to use this picture again. Here's our yaw rate. So that means that this wing is moving forward relative to this wing. Now that's forward and backward on top of the V infinity, but that wing is moving, has a higher velocity, forward speed, than this one. Because that wing's moving forward against the relative wind, so you get a higher relative wind over here, so you get an increase in angle of attack. No, sorry, you get an increase in dynamic pressure, which gives you more lift and more drag on this wing. And over here, you get less dynamic pressure. Put a delta on that. And so you get less lift and less drag on that wing. So what does that do to roll and yaw the airplane? So let's pull up the foam airplane again. It's yawing like this. You can see that this wing is moving forward and this wing is moving backward. So we get more lift here and less lift here. So the more lift here is going to roll the airplane positive, right? Okay, so let's stick with that in our mind for a minute. So a positive yaw rate gives a positive rolling moment or rolling moment coefficient. How about yawing? So this is due to the lift difference, because it's the lateral moment arm times the lift that gives you a roll. Okay, how about the drag stuff? So let's get rid of our velocity vectors here, because I've already put their effect here. So here we've got a bigger drag vector than over here. So what does that do? We've got a net yawing moment, right, in the negative direction. So a positive yaw rate due to the drag difference gives us a negative yaw. And we might as well write the side force up here. Oh, that's the vertical tail effect, never mind. So we get this happening. We've had a yaw, airplane's yawing this way, and we're gonna get a negative yaw as a result. We got that from the vertical tail, and we get it from the wing. So is this good, bad, or just ugly? What do you think? Airplane's yawing like this. We get a yawing moment in the opposite direction. That sounds good, doesn't it? Because it's going to oppose the yaw rate and damp it out, slow it down. So this is good. And we get that both from a vertical tail being above the CG, as well as the wing. So how about this? This says a yaw rate produces a positive roll. So the airplane yawing, both due to the vertical tail and the wing, is going to want to roll positive, which is this way. Is that good, bad, ugly? What do you think? I'm giving you guys more choices than if you get the chance to vote in the election next Tuesday. There, it's either one guy or girl, or one guy or another guy or a woman, right? Here, I'm giving you the option of none of the above. So which is it for that? Is there any stability effect of rolling related to a yaw rate? Doesn't really roll away from the yaw rate. It just rolls. So the answer is not really ugly. It's a side effect. Or that coupling that we were talking about last time. The same thing with a rolling rate, which we were talking about last time. A roll rate produces a yaw. That's a side effect. And in fact, it's these coupling side effects that we talked about lead to a spin if you're stalled, or just weird motion. So this is, on this one, this sign is good. Up here, this is just a side effect. Like when you take an antihistamine for a cold, or it may create drowsiness, right? So as I kept saying in 514, you guys are not medical doctors, you're airplane doctors when you're done here. You're experts on airplanes and the effects. How about if the wing is stalled? So we're talking about the wing now. How about if we're stalled? Because we looked at this with regard to the roll. Is that going to change things? Hint, if you're ever asked if stall changes things, what should the answer always be? Yes, it does, right? Because stall's a huge change. So in a stalled wing, if this wing is moving forward, then that may change whether the wing is stalled or not. This is going to reduce the angle of attack. So it may flip the signs of some of this stuff, and we may get a lack of stability in this way as well. It's less pronounced than what we were looking at before, because with the wings going rolling, it's real obvious how this wing could stall more and this wing could unstall. Here, because it's more of a dynamic pressure effect, it's a little less easy to see, but the angle of attack can change on each of these and produce an effect as well. The major effector with regard to this is that if the wing is stalled, there's a huge weight coming off the wing, blanketing the vertical tail, and so you lose the vertical tail effect on the yaw damping. Because this drag difference is not as big as the vertical tail effect, because that vertical tail effect, the vertical tail sweeping around way back there produces a huge CNR. So if you remove that effect because of the wake of the wing, then that has a profound effect on its ability to have damping with regard to the motion. All right, let's jump back to our matrix then. So we've done this column, beta dot P, and we just finished R. And the aileron and rudder stuff we've already talked about when we talked about the steady state forces and moments. Right, we defined a positive aileron and how an aileron produces a roll and a side effect of a yaw. So those equations are back earlier in chapter 3. And the nice thing about this is he lists the equations that predict each one of these. So we're done here. We did this earlier, and we even did see the beta effect earlier. And so we just finished all of this, but this was enough. This is pretty complicated because of all of the coupling and the pieces and parts. So in the homework, you also need the force and moments due to the thrust. And he has a nice model in the book for that. In this set of equations, he says, okay, the thrust, x perturbation, depends only on forward velocity, non-dimensionalized, and angle of attack. So he's saying that the other variables in there, like pitch rate, doesn't affect this much for relatively normal pitch rates. And so it's just an alpha perturbation and a forward speed perturbation that gives you these effects. And then lateral directional, he's saying the only thing that really makes a difference for the engine is a side slip. And that makes sense because the air coming in the inlet of the engine at an angle as opposed to straight on could change the thrust. So he goes through a derivation. The derivations with respect to the u over u1 look exactly like what we did for the longitudinal, because you have a derivative of whatever you're looking at, and then you have a derivative of the dynamic pressure. And remember, that's how we got those two parts that showed up in the equation, in the matrix. So there's nothing new here. It's just we're doing the thrust terms instead of the lift and drag and pitching moment. So I'll let you look through that. And when it's all done, you get these matrices. And that's what you're using in the homework. And so here you can see we get the double term because this is the derivative with respect to u, and then this is the dynamic pressure derivative, just like we got before. Notice that a lot of these effects, he says, are small. Like the side force on the thrust due to beta is small. And that makes sense because a small beta is not going to change the side component of the thrust because most of the thrust is pointing forward, not sideways. Same thing with rolling moment. You don't get much roll from the thrust at all anyway. But there could be some yaw because the engines, especially if you have a twin engine aircraft and you have one engine on each wing, and the side slip could change the relative yawing thrust from that. So this is easy. The hard part is estimating these, and he has a couple charts in there that you can go through, whether it's a propeller or a jet engine, to estimate some of these values. But a lot of it's just a quick calculation to give you a ballpark figure for some of these. So that's the end of chapter 3, the small perturbation section. And we've done chapter 4, which is the steady state flight. So we're going to go to chapter 5, which is now the dynamics. We're going to learn how to solve the dynamics equations. So we're going to look at Laplace transforms because that's our tool for solving differential equations. So the first thing that you're going to do, depending upon how long it's been since you've done Laplace transforms, is to go to Blackboard. And you're going to look at two handouts. One is from a textbook by a guy named Kuo, and then the other one is in a textbook, Nice. And it's just part of the textbooks. It's the part about Laplace transforms. And if you're in AE607 now, you've already done this. This is your textbook, right? Pretty sure that it's still being used. So this is like chapter 2 in that book. So if you feel like you're up to speed, and I think it doesn't hurt to review Laplace transforms no matter what, because they're kind of abstract in how you solve differential equations, but they work. If you haven't taken a class like a controls class where you covered Laplace transforms recently, this is an easy read. I recommend this one. I've given you this other one because it has some nice Laplace tables in it. But make sure that you know how to Laplace a differential equation with initial conditions, and then how to inverse Laplace, especially using partial fraction expansion. And you guys in 607 have done that this semester, right? Now, we won't be getting into it as deep as you do in that class and all of the control theory and the controller design, but we will use it to solve differential equations, which are the small perturbation equations of motion. What I'm going to go over starting today is first order systems and second order systems. Which is still a review. You've seen this in a class in Laplace transforms or just systems or dynamics. But we're going to use the results of this because when we analyze the airplane equations of motion, we get different modes out of the solution. And they'll either be a first order mode or a second order mode, and we'll identify them as such. And then we'll analyze them with the results of the standard second and first order system analysis. So a first order system in the Laplace domain looks like this, where if you do it as a block diagram, F is the input and X is the output. And if you want to think of this as a mass, where a force is being applied and X is the position of the mass. And the dynamics are described by a differential equation that when you Laplace it, you get this, and it's first order because it just has a single power of S. And because of that, you get a single root of the denominator or pole of the system. And the unit step response of this comes from putting in a step input, which you remember is 1 over S in the Laplace domain. So this is an input where it's at 0 and then at some time like at 0. It steps up. And if you Laplace that, plug it into the definition of Laplace transforms, you get 1 over S. So if we plug that in up here, we can look at the time response, and then we analyze it. So the number that shows up here in the denominator, this A, determines the nature of the response. So if we plug in the unit step response, then you get S along with S plus A. And then the whole partial fraction expansion deal is really just saying that my computer died. So we're going to switch to the board. Thought I'd charged it up enough, but I guess not. I said that I can't get it to go away from this screen. Here we go. So let's go up to the board. And we're not going to get into this too much today because I want you to have time to focus on the exam and then read those handouts if you feel like you need to. But again, all of this is real basic Laplace transform stuff that you've done in differential equations and a controls class. So we had x of s with the step input. And we said, well, let's divide that up into two fractions that if we add them together, we get this thing. So it's just like finding a common denominator, right? If you add 1/2 and 1/3, you multiply the top and the bottom by 3 and 2 here, you get a common denominator, and you find out what these things add up to be. So it's going to be 4/6, right? Did I do that right? That's going to be 3/6 and 2/6. 3 plus 2 is 5. Gee. Right, so this is the reverse of this. This is like taking this thing and splitting it up into fractions that get added together. That's all we're really doing, and you learned how to do that already, so I'm going to assume that you know how to do it, or you'll go back and look at those handouts and remember. But the nice thing about this is that when we then inverse Laplace, the 1 over s turns back into a step input. And this goes to e to the minus at, and that's just in the Laplace tables. And so we see that this a shows up in the time response. And we define something called the time constant. Which is 1 over that pole or root, 1 over a. And it characterizes what this behavior looks like, because this is an exponential decay that starts at 1, because at t equals 0, it's e to the 0 is 1, and it decays down like this. And when it gets down to 1 over e, that's what we call the time constant, because if you plug in the time constant for t, you get e to the minus 1. Right, you see that if you plug in at x at t sub c is this thing, but we're just talking about this term here. You get e to the minus a times 1 over a. So you get e to the 1, and that's just 1 over e. E to the minus 1, sorry. So that's just a measure of how fast this thing decays in response to this step input. So whatever initial condition you're starting at, you kick on the force at time 0, it's going to slide over. This is a measure of how far it gets in a certain amount of time. And you can calculate, from that you can calculate what's called the rise time, which is the time to go from 10% to 90% of the final value. And you calculate the settling time. You can calculate that from A or the time constant. So if you have a system, an airplane or a banana manufacturing machine, I don't know what that would be, and you would say, okay, the rise time of my machine is 3 seconds, people can compare it to their machine and their rise time, and that just tells you how the system behaves. Or you specify your settling time, or you specify the time constant. And when we get to doing airplanes, and we look at the FAA specifications for how an airplane responds to disturbances like gusts and elevator inputs, if it's a first order mode, the FAA regs will say it has to have a time constant less than a certain value in order to have acceptable handling qualities. So we'll take the mode that we get for our airplane, that's the first order mode, we'll calculate the time constant, and then we'll compare it to the charts from the FAA, and that will tell us whether we have a good design or not. Okay, if you remember, some modes turn out to be second order instead of first order. So we'll review that next time on second order systems and how we characterize those. You probably heard, right, damping ratio and natural frequency. So those are the things that you go then look up in the FAA regs and figure out whether your airplane behaves properly or not. Again, those handouts are on Blackboard. The Nice one is the one I recommend, but make sure you look through the other one and look, there's a couple of Laplace tables in there as well. Okay, we'll call it for today. Have a good weekend. The weather is supposed to be nicer than it has been, so get out and enjoy it.